Welcome everybody to this webinar about lift-off processes. This is the first webinar about the pattern transfer, but not the last. There are a couple of more coming up. Actually, at Heidelberg Instruments Nano, our leading principle is that if you can make a pattern in the resist with the NanoFrazor, you should also be able to transfer that into any material that you desire. Now we have been working hard on that, and we have developed a broad range of pattern transfer processes that are compatible with normal cleanroom tools and processes. For example, it is possible to etch both 2D and 3D structures into the substrates. There will be a separate webinar about each of these topics later on in the series. Also, it is possible to mold, make replicas out of the resist structures, for example, for nano imprint mastering applications. Also, this will be covered in a separate webinar. Also, it's possible to assemble nanorods, nanowires, and so on by using templates patterned into the resist. But today's topic, as already mentioned, is lift-off, which is maybe the most commonly employed nanofabrication pattern transfer process. So just looking into Wikipedia, we find the lift-off process definition. So basically you can pattern a photoresist using any lithography technology you desire. The only requirement is that there should be a hole created in the resist where the bottom is exposed to the substrate where you want your final pattern to be, and there should be some resist left elsewhere. And so that when you deposit the metal, most of the metal typically remains on top of the resist, and the parts you want to stay are deposited onto the substrate. Then when you put your sample in the substrate, into the solvent or chemical, then the resist together with the excess metal will be removed during the process, and you will be left with only the structures that you wish to remain, that were deposited in the hole in the resist. The key here is that you have an access point or several access points for the solvent to enter to the interface between the continuous metal film on top and at bottom to actually dissolve the resist. Now we have a small problem with the NanoFrazor because we are using these ultra sharp heated tips for removing polymers from the samples, and we would end up, as we can see in this illustration, with sloped sidewalls. And if we would deposit metal everywhere on the sample, we would have a continuous film of metal, and the solvent could not remove the PPA from underneath. We would be just left with the original structure like that in the final sample. Now, to overcome this problem, we introduced an additional resist layer underneath the PPA. It's called the lift-off resist, or LOR for short, on top of which then we deposit the PPA, typically around 30 nanometers in thickness. However, there are exceptions to this. Then after patterning our desired geometry in the PPA, we carry out a wet etching step, which is typically a base, typical developer, or a solvent that is isotropically developing the lift-off resist underneath the patterned holes. So we have a nice undercut developing in the lift-off resist, which then helps us to get this continuous film after the evaporation. As you can see here, the metal top at the bottom, they are not connected. And when we put the sample in a solvent, the lift-off resist, PPA, and the excess metal are removed, and we are only left with the metal where we want it to be. In this SEM image, we see a cross-section of a bilayer lift-off sample just after the evaporation of the metal, and here we can indeed see that the metal here is discontinuous between the bottom and top of the resist, We also see the freestanding PPA film and a nice undercut that has been formed in the lift-off resist. Now, this kind of bilayer lift-off process can be applied to virtually any patterns you wish to transfer on your sample. It's particularly useful for example, creating ohmic contacts to 2D materials, talking about electrodes or straight electrodes, for example. What was done in this paper from Zheng last year was they used a layer of 200 nanometers of PMGI. PMGI is our typical lift-off resist of choice, coated with 20 nanometers of PPA, and underneath one layer of MOS2 grown by chemical vapor deposition. After that, the sample was imaged using the NanoFrazor tip, and the flakes were still very nicely visible through the entire stack of resists. And they could carry out a nice overlay of electrodes, and they removed the resist on desired locations. And the PMGI was developed with a diluted TMAH at 1 nanometer per second develop rate. Low develop rate is important so that we can control the undercut accurately. It's worth mentioning that during this process, the tip apex temperature is reaching only about 120 degrees Celsius, which is enough to decompose the PPA. And we estimate the temperature rise at the sample surface to be well below 10 degrees Celsius. So it's a very gentle process for sample fabrication. The paper reports record device performance with one-off ratio of 5 × 10⁹ and extremely nice subthreshold swing. What is most notable is that the Schottky barrier is vanishingly small, shown here. For the NanoFrazor pattern device, it's completely linear over a very broad voltage range, while as for the electron beam lithography fabricated samples with the identical electrode material and geometry, we see very coarse nonlinearities. The device itself looks like this: source and drain, and then there's a hexagonal boron nitride, top gate dielectric, and the top gate on top. All of the electrodes were patterned using a NanoFrazor and the bilayer lift-off process. One possible explanation why the devices perform so nicely could be that when we carry out AFM inspection of the MOS2 just after developing, so just before the metal deposition, the NanoFrazor samples are pristinely clean, so we don't see any modification of the material, while as for the electron beam lithography pattern sample, we see residues from the electron beam resist. It has, as we say, burned on the sample. We also see roughening of edges, which is quite clear damage, which we attribute to the electron beam lithography process. So what can be the limitations and challenges when we carry out a bilayer lift-off? So first of all, when we were starting to develop this process, we quite often observe this kind of halo image around our structures. So here we want to transfer these bright squares into the metal. What this turned out to be that the developer is water-based, while PMGI is quite strongly hydrophobic material, and the substrate was not treated silicon, so the native oxide was hydrophilic. And as a matter of fact, the developer wanted to penetrate between the PMGI and the substrates and push away to lift off the resist material. This is what we can see here. The solution to this is quite simple. So you have to just make the substrate hydrophobic to start with by treating it with HMDS before you spin coat the PMGI layer. The other limitation is that the maximum deposited metal thickness, we found it to be experimentally about 40% of the lift-off resist thickness. This is due to the fact that the metal tends to slowly creep from over the edges of the PPA towards the bottom. it ends up encapsulating the entire patterns, and the solvent cannot anymore enter to remove the lift-off resist. So what is the solution is again simple, just use a thicker lift-off resist layer, and we can continue with the thicker metal. But actually, as it turns out, this approach of making the LOR thicker limits the resolution as well, as I explain on the next slide. This is due to the fact that the isotropic development is actually determining the minimum distance between the openings in the PPA. And this is approximately 2 times the thickness of the LOR layer. It's explained best by this simple animation here. So as you can see, as we bring the openings in the PPA closer to each other, eventually the undercuts reach each other, and the PPA on top becomes freestanding, and it will fly away in the developer. And we end up having just a continuous field of metal instead of our line and space pattern. We pushed this technique a little bit, and we managed to pattern 70 nanometer resolution line space array by using 35 nanometers of PMGI and 20 nanometers PPA and a 60 nanometer metal layer thickness. It might be possible to push it a little bit more, making the PMGI a little bit thinner still, but the metal then would not be anymore very conductive. And actually, we have another process for high resolution liftoff, which I will explain in a moment. But actually, such freestanding bridges can also be taken advantage of for certain device architectures. Namely, the suspended PPA bridge, if it's made short enough, it can support its own weight, and it can be used as a shadow mask for evaporation, as explained here. So here the PPA bridge is supported by the LOR islands on both sides. The undercut has completely removed the LOR here in the middle, and what we are left with is this kind of a nano gap structure, which is defined by the PPA bridge. Using this approach, we have achieved to pattern less than 10 nanometer nano gaps between metal electrodes. Very useful structures for example, plasmonics devices. And another process that takes advantage of freestanding bridges is the so-called Dolan bridge process that is very widely employed in fabrication of different junctions for quantum computing applications, for example. Here we again start by defining a freestanding bridge. And the trick here is that we carry out evaporation with an angle. So we apply a tilt into the substrate during the evaporation of metal, and in this way we can evaporate metal underneath the suspended bridge. If the metal we evaporated is aluminium, for example, we just vent the evaporator, and a very thin and a very high quality oxide is formed over the aluminium electrode. We can continue the process by tilting the sample to another direction, and in this case then we can make a connection with the already evaporated metal electrode underneath the suspended bridge. The nice thing here is that the overlap can be very definedly tuned by adjusting the tilting angle. So we can fabricate using the same geometry different kinds of Josephson junctions with different overlaps. So we have also done this using the NanoFrazor. So the structure I showed before was mainly E-beam lithography based. But what is the main difference to NanoFrazor is that just the choice of materials, of course, that we use PPA on top, a little bit thicker this time, 100 nanometers, just to make sure our suspended bridge is stable mechanically. As a lift-off resist, we used a material called LOR5B. It's basically PMGI, but it develops a bit faster. And all this on a sapphire substrate. The LOR can also be developed using a TMAH, the AZ400K developer. In the optical image here on the left, we can immediately verify just by eye that we have created a freestanding PPA bridge here. The undercut is nicely visible as the bright rim around our patterns. And we also verified the dimensions and the condition of the bridge by SCM and AFM shown here on the right. Again, the major benefit compared to electron beam lithography is that you don't expose your sample to bombardment of electrons or other charged particles, which might trap there and then cause lots of problems when you are measuring your sensitive reception junction. So far I only spoke about PMGI, but there is also an alternative lift-off resist material, the PMMA copolymer. The MA stands for methacrylic acid. This material has 33% of methacrylic acid. It turns out it can also be used as a lift-off resist. It also gives us a nice undercut when it's developed. But why did we look into this material in the first place? Well, we have quite some requests from our customers who would like to carry out the entire device fabrication process in a completely humidity-free or water-free environment. Basically, a glove box, which we have developed, a custom-made glove box with M. Brown. And we need the PMMA MA for carrying out a completely water-free lift-off process. So it turns out that it can be developed with pure ethanol at a rate of 1.8 nanometers per second. It's actually just by chance perfectly suitable for our thicknesses of materials we are dealing with here. So in the glove box environment, one can carry out the entire sample spin coating and patterning, then developing, and the metallization and lift-off process completely in a water-free process. Interestingly enough, I also managed to achieve the smallest ever nano gap between metal electrodes using ethanol developing and PMMA MA. It might be a coincidence, or it might be a property of the material, I don't know. But anyway, this is done using the freestanding PPA bridge process that I showed before. Very quickly, a comparison of the properties of these two different materials. They have some small but important differences. So as I already mentioned, PMGI refers to, it would be better to use a hydrophobic substrate for it. So ideally HMDS priming is recommended. While the PMMA MA likes to stick on hydrophilic substrates, so ideally oxygen plasma. But if your sample is sensitive with sensitive materials, typically just native oxide on silicon is hydrophilic, and we don't have big issues with adhesion of PMMA MA. Developer for PMGI is a base, a water solution, while for the PMMA MA we can use either ethanol in the water-free process, or a mixture of IPA and DI water also works very nicely. For both of these materials, we recommend DMSO, dimethyl sulfoxane, as the remover for the lift-off process. I also want to mention quickly, as I referred before, we also have a process for transferring patterns that are less than 70 nanometers. And we call it very originally the higher solution lift-off process. In here we have, instead of 2 layers, we have actually 3 layers. So we have here PMMA as the lift-off resist layer. On top of that, we spin coat a very thin layer of silicon hard mask. So we developed together with the company PyBond a material we call SH113. It's basically a spin coatable siloxane polymer that is it's reduced into a silicon dioxide, but it's exposed to a gentle oxygen plasma, and it forms an extremely thin layer of silicon oxide, which is pinhole free and extremely smooth, only 1.5 nanometers thick. And on top of that, we spin coat PPA, about 10 nanometers typically. We want to make it as thin as possible so that we can also pattern using the maximum resolution enabled by the sharp tips. After the patterning, we first etch the patterns from the PPA into the silicon dioxide in a reactive ion etching step. Afterwards, we transfer the pattern further into the PMMA below using oxygen plasma in a reactive ion etcher. The silicon dioxide is, as I mentioned, it's a very high quality oxide, so it can withstand etching of even hundreds of nanometers of PMMA if required. In this case, the undercut that develops is much smaller than in the case of the bilayer liftoff. And we can actually evaporate up to 60% of the PMMA thickness in metal, and then carry out a liftoff by dissolving the PMMA in acetone. Here's an example structure, just a 6-fold bow tie antenna, where the tips have a radius of about 5 nanometers, and the gap between each of the leaves is less than 10 nanometers. This was a lift-off in gold. So actually for this process, the key features are its very high resolution. So it's a much higher resolution than the bilayer lift-off process due to the lower undercut. And also the feature density we can achieve is very much higher. However, it requires dry etching. And actually the 2D etching is handled in more detail in another webinar in this series. So stay tuned for that. So I want to show quickly a couple of examples made by the high resolution liftoff process. So first of all, here we have a device that was first fabricated by electron beam lithography, these gray electrodes. And then we overlaid and patterned these very narrow top gate electrodes on top using the NanoFrazor. And there's a very thin alumina oxide dielectric in between. Another example, which is also actually a mix and match with electron beam lithography and NanoFrazor. These pads here were defined with electron beam lithography, and these very narrow electrodes were overlaid on top with the NanoFrazor. These are only in the range of 10-20 nanometers wide lines, however, they are electrically conductive as verified by electrical measurement. The limitation of the high resolution liftoff is the pattern collapse. As you can imagine, if you have a very thick PMMA film and very high resolution pattern, then the aspect ratio of your structures, that is the height divided by the width of them, becomes higher, and the tendency to pattern collapse is actually directly proportional to the square of the aspect ratio. And here we can see in these images where the aspect ratio is slowly increasing, and we can also see the amount of pattern collapse becoming more and more dominant. And from top, the structure looks like this, and this is not very useful anymore for the liftoff. So the lecture learned here is that if you want to make very high resolution metal lines, you should make them very thin. And in other words, if you want very thick metal lines, then don't make them the metal very thick. Sorry, they don't use a very high resolution, of course. Okay, in conclusion, I showed that the liftoff processes are compatible with the NanoFrazor patterning. So we have these two processes, the bilayer liftoff. It's a very straightforward, quick, easy to use process. It's also very gentle. It enables making contacts with minimum invasiveness to your sensitive material. And as a bonus, it can be also made completely water-free in a glove box environment. I also showed that if the resolution of the bilayer liftoff is not enough for some application, there's also the higher resolution liftoff, where we use a 3-layer pattern transfer stack that can be entirely spin coated. We can reach very high resolution, but it does require reactive ion etching, so it's a little bit more complicated. But actually, if you refer to the NanoFrazor process handbook, which will be an additional feature in the latest software version, which will come out soon, it will contain much more detail than I have shown here about the processes and also all the materials involved. So I'd like to thank you for your attention. Thank you for listening to me, and I look forward to answering your questions.